This video is a continuation of my lecture tutorials on analyzing test questions on mechanical waves. So this time, I'll be discussing questions pertaining to speed of transverse mechanical waves, uh, such as standing waves produced by stretched string, and also I'll be discussing about questions related to shock waves. Question number 1. One end of a 2 kilogram rope is tied to a support at the top of a mine shaft 80.0 meter deep. The rope is stretched tightly or taut by a 20.0 kilogram box of rocks attached at the bottom. Letter A. A geologist at the bottom of the shaft signals to a colleague at the top by jerking the rope sideways. What is the speed of a transverse wave on the rope? Letter B. If a point on the rope is in transverse simple harmonic motion with frequency f equals 2.00 Hz, how many cycles of the wave are in the rope's length? So as shown in this diagram, uh, the length of the rope, okay, that is used here is the same as the depth of the mine shaft, which is 80.0 meter. And the person at the bottom will be creating a wave pulse by jerking the rope sideways. Okay, and we assume that the wave pulse that is produced behaves like a simple harmonic motion, whose frequency is given at 2.00 Hz. And because there is a 20 kilogram box of rocks that is attached at the bottom of the rope, so it makes the rope stretch tightly, okay, uh, and the wave pulse that is going to travel from the bottom of the rope, okay, in the direction upward until it reaches another person, okay, at the top, exactly a distance of 80.0 meters. That's equivalent to the length of the rope. So our first task is to determine the speed of the wave pulse, a transverse wave that is created in the rope. Okay, so we are also uh, going to determine the number of wavelengths or the number of cycles of the wave produced in the rope. So our first question, solution to our first question, we first determine the tension F that is exerted on the rope, and that is just equal to the uh, product of the mass of the rocks that is attached at the bottom of the rope, of course, multiplied by acceleration due to gravity, 9.80 meters per second squared. So 20.0 kilogram times 9.80 meters per second squared will give us a tension force equivalent to 196 newtons. Alright, after getting the tension, we also determine the linear density mu, okay, which is the what we call property of the rope. Okay, linear density is specifically also called the mass, linear mass density, and that is determined by just getting the ratio of the mass, all right, the mass of the rope divided by its length L. Alright, so 2 kilograms or 2.00 kilogram divided by 80.0 meters will give us the value of 0.0250 kilogram per meter. Alright, that is what we call the linear mass density of the rope. So these two quantities, the tension in the rope as well as the linear density of the rope, okay, will be our basis in determining the speed of the transverse wave that is produced on the rope. So we use the formula V is equal to the square root of the force F, the tension in the rope, divided by its linear mass density mu. Substituting, we have square root of 196 newtons divided by 0.0250 kilogram per meter, and our answer is the speed of the wave is equal to 88.5 meters per second. Okay, so for letter B, uh, we're going to determine the number of wavelengths or the number of cycles, complete cycles produced in the ropes, whose length is given 80.0 meter deep. Alright, so our formula for determining this is simply in terms of the relationship of the wavelength lambda, alright, which is equal to the speed of the wave divided by its frequency. Okay, so that means 88.5 meters per second, that is the speed of the wave, transverse wave, divided by its given frequency, which is 2.00 per second, or hertz. So our answer for the number of wavelengths, or the wavelength of the transverse wave itself, is equal to 44.3 meters. Alright? But since we're talking about the number of cycles that is produced, the number of wavelengths, one complete cycle has a wavelength of 44.3 meters. But since the length of the rope is 80.0 meters, that means we are going to divide it by the wavelength, which is 44.3 meters, and we will get as our final answer, okay, the number of cycles being equal to 1.81 cycles. Before we proceed to question number 2, let's first talk about standing wave. How is standing wave produced in a string? Alright, so we have here an illustration that shows a string that is fixed at its left end while the right end is being moved up and down. Okay, so when this string is moved up and down, a wave pulse is produced. Okay, that is going to move to the left. Okay, so upon reaching the other end, okay, the wave pulse is reflected. All right, and when the incident wave from the right end meets with its reflected wave pulse, there will be a what we call interference that's going to happen. The combination of two waves having the same wavelength, frequency, and if they are exactly in phase, they are going to produce a much bigger wave, bigger in amplitude compared to the original waves. So this four patterns show you the possible wave patterns in a given standing wave. So in the first one, the string is equivalent to 1/2 wavelength. All right. The second pattern shows a string, the length of the string is exactly equal to 1 wavelength long. While in the third pattern, we have a case where the string is 1.5 of a wavelength long. And in the fourth pattern, we have a case where the length of the string is equivalent to 2 wavelengths. Now in here, this is a snapshot of the wave pattern shown in letter B, wherein the string is taken at two different points or time. Okay, this one, okay, the boulder curve shows the wave at a certain time, and then half of the period, okay, is also the position of the rope, okay, and this is appears to be a wave that doesn't move either to the right or to the left. It seems that the string has remained stationary, and hence the word standing wave. Right? Take note that uh, the letters here denoted as capital N refers to the part of the wave cycle corresponding to the particles in the medium, such as the string, where they are never in motion. So we call this the nodes. Okay, it's understood that the two ends of the rope are considered the nodes, and the one at the middle is also a node. So this is the case where we have three nodes, and the point exactly halfway between two consecutive nodes is what we call the antinode. And the antinode represents the amplitude that is maximum or corresponding to the maximum displacement of the rope. So when there are three nodes, it follows that there are two antinodes. Okay, remember N stands for the node and capital A stands for the antinode. Question number 2. While a guitar string is vibrating, you gently touch the midpoint of the string to ensure that the string does not vibrate at that point. Okay, the question is which normal modes cannot be present on the string while you are touching the string of the guitar this way. Alright, so again, we have the illustration of the wave patterns when there is standing wave, okay, occurring in this string. When both ends of a string whose length is L are held fixed, standing waves can occur only when the length L is an integer multiple of lambda over 2 or half lambda. Right? So each frequency with its associated vibration pattern is what we call the normal mode. So each of these, all right, pattern is what we call the normal mode. The simplest type of mode is a case when there's only one antinode. All right, the midpoint of the two nodes is an antinode, and that corresponds to 1/2 lambda being equal to the length of the string. When there are two antinodes, all right, so the one in the middle or midpoint of the length is a node, okay, and this wave pattern corresponds to 2 1/2 lambda, or exactly equal to 1 lambda being equal to the length of the string. Now, for the third pattern, we have 1, 2, 3 antinodes, okay, including the one in the center is an antinode, and the length of the string happens to be equal to 3 half lambda or 3 halves lambda, while the fourth pattern has 1, 2, 3, 4 antinodes and 5 nodes. And this is equivalent to a length of the string being equal to 4 half lambda, or exactly to lambda, or twice the wavelength. All right, so the relationship of the number of antinode to the length of the string and the speed of the standing wave is shown in this simple formula or equation, where Fn represents the frequency of each wave pattern. For the lowest frequency, we call that the fundamental frequency. All right, that means the number of antinode, capital A, is equal to 1. All right, so when we multiply the number of antinode to the ratio of the speed of the wave divided by twice the length of the string, that gives us the corresponding frequency. Okay, but n can either be 1 antinode, 2 antinodes, 3 antinodes, and so on and so forth. Okay. This formula is only for a string that is fixed at both ends. Okay, so the term used for the smallest uh, smallest frequency possible, we call it the fundamental frequency, and they also call it the first harmonic. For F2, meaning the second fundamental frequency, is known as the second harmonic, and the third fundamental frequency, F3, is called the third harmonic. But among musicians, the term that they use corresponding to the second harmonic is what they call the first overtone. Okay, the third harmonic is what they call the second overtone, and so on and so forth. But going back to our question, what happens if the guitar string is touched while it is vibrating? You're going to touch it at the midpoint of the string. Okay, so what patterns cannot be present on the string when you do this action of touching the string while vibrating at exactly the middle point? Right. So our answer is all cases or all wave patterns where the number of antinodes are odd integers, such as 1 antinode, 3 antinodes, 5 antinodes. Why is that so? All right. When you touch the string at its center, you are actually producing a node at the center, right? Like what you do in the second pattern. So when the antinode is at the very center, that corresponds to a length of the string being equal to lambda, or 2 half lambda. Okay? So uh, that's the first case. The second case is when the length of the string is equal to twice the wavelength lambda, or when you have 4 half lambdas. 4 divided by 2, that makes it 2 lambda. So those are the cases that we want in this question, because we are looking for the normal modes that cannot be present, or that cannot happen, okay, in the string when it is touched at its midpoint while it is vibrating. Only those cases, or uh, what we call only those normal modes whose number of antinodes are even numbers, like 2, 4, 6, and so on. For instance, the first pattern, which corresponds to our first harmonic, all right, or the fundamental, where n is equal to 1. Okay, here, this is a case where uh, our standing wave, okay, is such that the length of the string is just equivalent to half lambda. So this is a possible normal mode. Okay, okay, that's possible, that will happen. Okay, or that can be present, and The third one is also possible because the antinode is the one in the middle. Okay? And if we have a fourth or a pip case where, again, the antinode is the one in the middle. Okay? I hope you are not confused because the question is looking for the normal modes that cannot be present on the string when you're going to do this action of touching the vibrating string at the very center. All right? Touching the string at the very center while vibrating creates exactly a node at the very center. And that's true for pattern number 2, pattern number 4. So that means those normal modes cannot possibly happen, okay, in this particular action specified in question number 2. Question number 3. A cable is stretched between two posts 3.00 meters apart as shown in this sketch. The speed of the wave on this cable is 96.0 meters per second and the tension in the cable is 175 newtons. If a standing wave on this cable has 5 antinodes, okay, as you can see there are 5 loops or 5 antinodes, 1, 2, 3, 4, 5. Question letter A, what are the wavelength of the standing wave? Letter B, okay, uh, what are the frequency of the standing wave and the linear mass density of the cable? All right, so our first answer or solution to question letter A, finding the wavelength, the standing wave, looks like we must determine first the frequency of the standing wave. All right, using the formula that we earlier showed, where Fn is equal to the number of loops or antinodes n multiplied by the ratio of the speed of the wave divided by 2L. All right. Uh, if you notice that V over 2L is just actually um, represents the when you divide, right? When you divide the speed by the corresponding wavelength, all right, or whatever is the length of the string, one half of that, okay, is the relationship between uh, the frequency, okay, to that wavelength, okay. So this is very important in determining uh, the frequency of the given what we call standing waves. So since there are 5 antinodes, we just indicate n equals 5. We are given the speed of the standing wave 96.0 meter per second. So we just multiply them and then divide them by twice the length of the string or cable. All right. So when you simplify this, we get the frequency Fn equals 80.0 hertz. So knowing that particular frequency of the standing wave, we can now determine the lambda or the wavelength. That's the question in letter A. That's just equal to V over F. All right. So 96.0 meter per second divided by the frequency 80.0 hertz, we get lambda or wavelength equals 1.20 meters. All right. So what about letter C? Determining the linear mass density of the cable. So earlier, we also showed the formula that relates the tension force F to the speed of the wave and to this quantity called linear mass density. So our solution is or goes like this. We first determine the fundamental frequency or F1. All right. F1 is just equal to the frequency of the standing waves with what we call 5 antinodes. So the frequency, fundamental frequency, meaning the one corresponding to just one antinode, we just divide. Okay, F5 or F5 is what we got earlier. All right, 80.0 hertz. Okay, divide it by 5, then we get the fundamental frequency F1, which is 80 divided by 5, and that is 16.0 hertz. This is what we are going to use, okay, to determine the linear density or mass density. Because what is used in this formula is the fundamental frequency F1. All right. That's why we don't use the Fn equal to 80.0 hertz. Instead, we use 16.0 hertz. This corresponds to the value of the fundamental frequency. So, from this formula, F1 equals 1, 1 understood to be the number of antinodes. All right? Divided by twice the length of the cable, and then to be multiplied by the square root of the tension in the cable, or F, divided by the linear mass density. But since what we are looking for is the linear mass density, so there is a need for us to transpose this equation, simplify it such that we will have our linear mass density on one side of the equation. Okay, and that becomes something like this. Mu will be equal to the tension F divided by quantity 2L times F1 quantity squared. So we got to square, okay, the product of 2L and F1 before you divide F. Okay, or that is as shown in our substitution. We first write down value of F, which is 175 newtons, and then get the square of 2L F1, where of course the length uh, the length of the cable is given, all right, equivalent to 3.0 meters. That's the distance between the two posts. So that means that is the length of the cable. Okay, getting the square of that length, that's how we got 9.00 meters squared. Of course, the square of 2 is 4. And the square of F1, which is 16.0 hertz, is 256 per second squared. All right? So, I hope you understand how we got these quantities. 4 multiplied by 9 meters squared multiplied by 256 per second squared. That is the result of getting the square of 2, the square of the length L, the square of F1. Then if we multiply them all, okay, what we get is 9,216. The unit, of course, becomes meters squared divided by or per second squared. So this is the time that we can divide 175 kilogram meter per second squared. That is the equivalent of Newton. Okay, 1 Newton is equal to kilogram meter per second squared. There is a need for us to break down Newton into kilogram meter per. so that we can see, okay, uh, what will come out as our final unit for our linear mass density. All right. So dividing 175 by 9216, okay, our numerical value becomes 0.0190. And you notice the meter in the numerator cancels, okay, and that leaves us meter in the denominator, while the second or the per second squared, that's the meaning of second raised to the negative 2, that's per second squared, that simply cancels out. And our final value and unit for the linear mass density mu is equal to 0.0190 kilogram per meter. As you can see, kilogram is a unit of mass, and meter is a unit of length. That's why it's called linear mass density, all right? Because the mass is expressed as per unit length, not the usual mass per unit volume. Okay, mass per unit volume is the usual volume density of a body or substance. But here we're talking about linear mass density. Okay, the amount of mass per unit length. All right, so we are done with answering our uh, question number 3. Before we discuss our last question, which is all about shock waves, we first describe what we mean by a shock wave. All right, in our past discussion about sound waves, we have introduced the phenomenon, the Doppler effect, and we said that uh, the frequency that is observed by a listener, okay, changes or is different from the actual frequency of the source. That's true if um, both the speed of the listener when it is moving and the speed of the source when it is also moving are uh, pretty less as compared to the speed of sound. Question now therefore is, what's going to happen if the speed of the source that's creating the sound becomes greater or higher than the speed of the sound itself? All right, so such phenomenon where a special kind of wave is produced as a result of having a source of the sound that is moving faster compared to the speed of the sound. Okay, that is exactly what we mean by a shock wave. And when you're going to illustrate, okay, this is how it happens. So supposing we have here an airplane, the airplane is moving uh, nearly the speed of sound, as you can see here. All right, so it's moving from left to right. Its Vs, or the speed of the airplane, is such that it is almost, okay, approaching the speed of the sound that is created. All right, we say that the wave crest, okay, in front of the airplane sort of pile up. Okay, this sort of pile up, uh, and what happens is this crest, okay, will be some sort of, they get compressed. All right, so when they get compressed, it comes to a point when the airplane has to exert a force, okay, a force uh, on the surrounding air. Okay, such a large amount of force has to be exerted by the airplane, by that nose of the airplane, because the resulting resistance coming from the air, okay, becomes so high and so strong. Okay, that is the case when the airplane is about to break what they call the sound barrier. Okay, sound barrier. So, what happens if the speed of the airplane goes beyond the speed of the sound itself? This is not the case, all right? The sound source, meaning the airplane, is now moving faster than the speed of sound. So, what is created is a wave known as a shock wave. And the wave front of this shock wave is like a cone. Okay, it's like a cone. It's supposed to be three-dimensional, right? And that angle that is formed, okay, by the what you call shock wave, the wave front of the shock wave, labeled here as the one colored green. Okay, this is the result of the wave fronts created. All right, as a result of the interference of all the shock wave produced as the airplane breaks the sound barrier. Take note that shock wave is not only produced at that instant when the airplane breaks the sound barrier. Okay? More and more shock waves are produced for as long as the airplane is moving faster than the speed of sound. And the net effect is to produce this wavefront colored green. Okay? And the angle that is formed by that line, labeled here as angle alpha, okay, is related to the speed of the sound and the speed of the source, okay, in this manner. The sine value of that angle alpha is just equal to the ratio of the speed of sound divided by the speed of uh, the source, meaning the airplane. So that is the relationship between this angle alpha and the ratio of the speed of sound to the speed of the source. All right. And a number known as the Mach number. Okay. Mach number has been given that term referring to the ratio of the speed of the source, such as the airplane, divided by the speed of sound. So that ratio, Vs over V, is given a particular term known as the Mach number. So the Mach number also tells us how many times is the speed of an airplane greater than the speed of sound. For example, if we have an airplane or a super jet plane, okay, whose speed is twice the speed of sound, okay, then the Mach number of that jet plane is equal to 2. Mach 2, okay, describes the speed of an airplane, a very fast moving airplane, whose speed is twice the speed of sound. Mach 2. That is the meaning of this quantity or term known as Mach number. All right. Uh, that is taken, this relationship, the sine alpha, is taken from this imaginary, what do you call, right triangle. Okay. as you can see here, the opposite side of that angle is the product of v times t, where t is the time. All right, and the adjacent side, um, this is the adjacent side. All right, in the diagram, and that is our hypotenuse. So if we define sine of that angle alpha, we just divide bt divided by the hypotenuse. Opposite divided by the hypotenuse gives us the sine of the angle alpha, and that pertains to the ratio of speed v, the time cancels out, speed b divided by vs. So that is the origin of this relationship, sine alpha equals b over vs. Okay, and then we get the reciprocal of the sine value of that alpha, meaning the reciprocal of v over vs turns out to be vs over v, and we give a name to that, which is the Mach number. Okay, we have our first example of a problem on shock wave in the next slide. All right, question number 4. What would you hear if you were directly behind, meaning to the left of, the supersonic airplane as shown in the figure? Okay, so as shown, here's the supersonic airplane moving at a speed of Mach 1.75. All right, the speed of the source, as indicated by this vector arrow, all right, is much faster than the speed of sound. Of course, that's why it's called supersonic. All right, jet plane. Now, as described earlier, the shock wave produced forms a three-dimensional cone. Okay, and if there is a listener who happens to be within that cone or inside the cone, such as this particular listener, all right, this particular listener will be able to observe, okay, this shock wave. The sound that is created as a result of shock wave is what we call a sonic boom, actually, you know. So the question pertains to a situation where the listener, if you were directly behind or to the left of the supersonic airplane, meaning if this is the airplane and you are here at this particular point behind, exactly directly behind uh, the moving supersonic airplane. All right, that is what the question is uh, assuming. A listener at this particular point, what is he going to observe? All right, letter A, a sonic boom. Letter B, the sound of the airplane that is Doppler shifted to higher F. Letter C, the sound of the airplane that is Doppler shifted to lower frequency F. Or D, the listener will not hear anything. All right, so he hears nothing. Which is among these four choices is the best answer? All right, so our analysis is this. The figure, uh, as shown, okay, there are waves inside the cone of the shock wave. All right, imagine those circular wave fronts that form the three-dimensional cone. So behind the airplane, the wave crests are spread apart, as you can see. All right, the distance between the crest is larger, bigger as compared to those at this point. All right. So if you are there exactly behind the airplane, the waves that will be reaching you would have an increased wavelength. Longer wavelength corresponds to a lower frequency. So, our best answer to that question, of course, will be letter C. The sound of the airplane can be heard by this listener exactly behind the airplane, but the frequency of the sound he hears is shifted to lower frequency. Alright? So for this listener being described, the Doppler effect phenomenon is going to exist, or he will be uh, he's going to hear a Doppler shifted sound of lower frequency. So that's the answer to our question. Now, in addition, supposing there is a listener to the right of this particular listener over here, all right? This particular listener labeled L here will also experience, okay, or will be able to hear a sonic boom, all right? A sonic boom, which is the result of the shock wave reaching this particular listener. Okay, but if there is another listener to the right of this listener here, maybe, for example, a listener at this particular point, that particular listener at this very instant will not hear anything, all right? But in a very short while, as the airplane continues to move to the right, then he will be able to hear a sonic boom. Okay, just like the first listener we're referring to here. Those listeners to the left of this particular listener have already heard, okay, the sonic boom, all right? Because the plane has already passed those listeners and they already have experienced the shock waves, okay, by hearing the sonic boom. So that is how we interpret, okay, the effect of a sonic wave. I mean, a sonic boom produced as a result of the shock wave produced by the supersonic airplane. Our last question, question number 5. An airplane is flying at Mach 1.75 at an altitude of 8,000 meters, where the speed of sound is 320 meters per second. How long after the plane passes directly overhead will you hear the sonic boom? Alright, so assume that you are the listener and you're on the ground, of course. Then there's an airplane, a supersonic airplane flying at 1.75 Mach at an altitude of 8,000 meters. Right? So, what is asked is the time after the plane has passed overhead, how many seconds will you be able to hear the sonic boom? Alright. So, we first determine the angle alpha. Earlier, okay, we mentioned that the uh, angle alpha, okay, or the sign of the angle alpha is related to the ratio of the speed, okay, the speed of the source and the speed of the wave. All right. So here we modify the equation so as to be able to find the angle alpha in terms of the arc sign, okay, of the ratio or reciprocal of the Mach number. Remember, the Mach number is the ratio of the speed of the source, meaning the airplane, divided by the speed of sound. And the reciprocal of that, okay, if we get the sign of that reciprocal, then we can use this formula to find the angle alpha. Alright, so with the help of your cycle, turns out that the angle alpha is equal to 34.8 degrees. Okay, so knowing that the angle alpha is 34.8 degrees, we can proceed in determining, okay, the speed, exactly what the speed in meters per second, the speed of the airplane, given its Mach number, 1.75, just multiply it by the speed of sound, which is 320 meters per second, and we will get 560 meters per second. That is the speed of the airplane moving at 1.75 Mach if the speed of sound, okay, is 320 meters per second. All right. What we are looking for is the time it takes for you to be able to hear the sonic boom. Okay, the time exactly after the airplane passed you overhead. Okay, so to do that, we use the fact that time is equal to distance divided by the speed. All right, and from here, okay, the value of tangent alpha can also be expressed as the ratio. All right, that angle alpha, okay, by definition in geometry, that also equals this angle here. All right, the angle formed by the horizontal, okay, with the wave front of the shock wave. That's also alpha. And from there, we can define that tangent alpha is equal to the altitude, 8,000 meters, divided by this adjacent side, which is just the product of the time t and the speed of the airplane vs. All right, and vst, because we don't know yet the time t, that is what we are going to isolate. Okay, the time t will now become, or will now be equal to the altitude 8,000 meters divided by 560 tangent of the angle 34.8 degrees. So using your cycle again, we will be able to calculate the value of the time t, which is equal to 20.5 seconds. So that is the time that you will have to wait, okay, after the airplane has passed you overhead. Okay, it takes 20.5 seconds before you will be able to hear the sonic boom. And for those who have experienced, okay, listening to a sonic boom, that's really the case. Long after the airplane above has passed, okay, it takes a while. In other words, it takes a while before you will be able to hear a cracking sound known as the sonic boom, which is the effect of the shock wave produced by the supersonic airplane. All right, so that is our answer to this question. In reality, by the way, in reality, okay, the speed of sound actually varies depending on the altitude. So here we assume that the speed of sound is constant at 320 meters per second. But, well, for simplicity, that's what we assume. But in reality, all right, in reality, uh, what do you think happens to the speed of sound as it approaches the listener? All right, so probably at a much greater altitude, okay, uh, or at a lower altitude, we can imagine that the speed of sound, all right, will differ from what we is assumed here as 320 meters per second. So out of simplicity, we just assume that the speed of sound doesn't change, okay, as it travels that distance, okay, or from an altitude of 8,000 meters. When it reaches the listener, okay, the sonic boom that he hears uh, is dependent on the speed of sound. All right, so this all uh, about shockwave. So thank you very much for watching.